All right, we are in Chapter 5 and continue to be in Chapter 5, still looking at trigonometric functions. And now we come to something called right triangle trigonometry. And if you have been in geometry class in high school, this probably is a good transition into the trigonometry state if you haven't seen this yet. But let's go for it. We're going to define trigonometric functions for acute angles, and then we're going to evaluate them. So we'll take a look at a few things here, and then we're going to look at basically two very special triangles here. We're going to look at the 45 45 90 triangle, then we're going to look at the 30 60 90 triangle, and those we're going to apply for the later on sections as well. Very important part right over here. You have to understand the book presents it one way. I'm going to present it both ways, or two different ways. All right, then we're going to try to look at some application questions as well. All right, first things first, we got to think about the whole concept of a triangle here. And so right away, what we really have to do is we have to think about which angle are we going to be looking at from. So notice this is a triangle ABC, but we have some special character here. We have the theta, and we have this little curve for our angle. And that really is talking about the fact that we're looking from angle A. Trying to think of it from angle A. All right, so from a long time ago, I'm pretty sure it was Ptolemy, a long time ago, he was looking at a triangle, and he pretty much asked himself, you know what? This really are ratios. Really, you have ratios here. You have this opposite side right here, opposite side. You have an adjacent side, which is touching this angle right here, touching this angle. And then you have this hypotenuse, and the hypotenuse is always the side that's opposite your 90-degree angle. And so what he said, you know, I can really make 6 different ratios here. I can look at this thing called the opposite side divided by the hypotenuse. I can take a look at the adjacent side divided by hypotenuse. And I can also look at opposite side divided by the adjacent side, and then I can take a look at all their reciprocals. So this is what this says. So opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent, and then the flip of these. So let's flip the A and the B, flip the B and the C, and then flip the C and the A. So he discovered, you know, there's really 6 different ratios I can set up. So over the years, these have now become called different units. Of course, it was not always named the same. We took a few years to go through this process here. But right now, we say this first one here. It's technically called sine. It's S-I-N-E. The sine, and then whenever you say sine, abbreviation would be S-I-N, and then we have the angle measurement. So it's always going to be sine of something. You always want to have an angle measurement after that. Okay, by definition, the sine value is the ratio of the opposite side over the hypotenuse, so A over C. Then there's something called cosine. And notice what we're going to do is we're going to take the first 3 letters, the COS, and we're going to take the angle measurement here, and again, it is adjacent over hypotenuse by definition. And again, you probably want to memorize these here if you don't know them already. All right, and then we have tangent. Tangent is going to be the ratio of the opposite side over the adjacent side, so A over B, and again, we're using the first 3 letters as well. All right, then we have the reciprocal of sine, and we call this cosecant. Well, here's my little problem. Once you label it as cosecant, or you call it cosecant, if you take the first 3 letters, what's going to happen is you're going to have the same thing as cosine, which is right over here. And so what mathematicians decided to do was really just to use CSC as the abbreviation. And then we have something called secant. Secant is going to be the hypotenuse over the adjacent, or the reciprocal of the cosine. And again, this one works well. I can use the first three letters. I haven't used those before. And we have cotangent. Cotangent, again, reciprocal of tangent, and this time I can use the first three letters as well. So really the only one I can't use the first three letters for is cosecant. And I'm sure you guys are now asking, so why do you have a co and like this, like cosecant, secant, and then this one is like cotangent, tangent, sine, cosine. We'll get to that a little bit later. They're called co-functions of each other. All right, but you need to know the definition pretty well for each of these here. Write them down if you don't. I'm sure by the end of this chapter you'll have it memorized anyways. All right, so we go on to now find the exact values of the 6 trigonometric functions of an acute triangle, which is a right triangle, assuming that the length of the opposite side is 4 and the length of the hypotenuse is 5. So let's go for it. All right, setting up a little triangle here. Then would be this. Label the fact that it is a right triangle by the little box there. And we're going to label this as 4 on this side, 5 as the hypotenuse, and here's a little problem already. We're missing one of the sides. And so what we're going to do is we're going to just label this as an A. And of course, now we have to figure out what A is. And I think you guys know what to do here. Since you have a right triangle, something called the Pythagorean theorem identity works just well. So we're going to use that to figure this out. So remember, the theorem says that if you take one of the legs squared and you add it with the other leg being squared, you will end up getting the hypotenuse squared. That's exactly what we're going to use to figure this out. So squaring the numbers that we can gives us 16 over here, gives us 25 on the other side. Subtracting both sides by 16 gives us 9, and if you square both sides, you get yourself a 3. Sorry, square root both sides. Notice also I'm not doing the negative or positive on it because the length of any triangle has to be positive, or the sides of any triangle has to be positive here. So there's no point of doing a positive or negative square root of 9. You just write 3 and you're good to go. All right, let's label this here. A equals 3. And we're ready now to set up for our trig functions. All right, the sine theta, and I guess we should label where theta is. Label theta is right here. We should have probably even labeled it a little earlier because you got to figure out which angle you're looking from. So if 4 was our opposite side, that means theta had to be here. But just to label it, just to make sure we got it. All right, and go with it. And so sine is opposite over a hypotenuse, so it's going to be 4 over 5. This part is easy here. You're just reminding yourself of the definition here. Cosine of theta equal to, now it's going to be the adjacent over hypotenuse, in this case 3 over 5. Tangent of theta is going to be opposite over adjacent, so opposite is 4, adjacent is 3. Those are the first 3 trigonometric functions, and these tend to be the more important ones. If you know these, you're in good shape here, but we should know the other 3 as well. Label that theta here just to make sure we got it here still. All right, cosecant theta. Cosecant theta is going to be the reciprocal of sine, or it's going to be by definition hypotenuse over opposite. All right, secant theta by definition is going to be hypotenuse over adjacent. And cotangent by definition, even though it's really just the reciprocal of 4/3, is going to be adjacent over hypotenuse. And there are our 6 trigonometric functions. All right, next we're going to try to write down or connect as many of these trigonometric functions to each other by means of identities. And so we have two different types of identities. One is called a reciprocal identity. The other one's called a quotient. Let's start off with a reciprocal identity. So we start off trying to see what we want to prove here. Let me just do 1, for instance. So you say 1 over cosecant. By definition, isn't cosecant going to be, let's see, put the 1 on top still, isn't that actually hypotenuse over opposite? If that's the case, in order to simplify this, don't we really just take the reciprocal and multiply? And in this case, we're just going to multiply this by 1, and if you say 1 times a over c, it's just going to be a over c. But then we ask ourselves, you know, don't we have another trig identity that is a over c already? And yes, it is. It is sine of theta. So then we've developed this reciprocal identity. We say, you know what? We now know that sine of theta is equal to 1 over cosecant theta, and we got ourselves an identity. There it is. There's one of those reciprocal identities. Of course, we could take a whole bunch of time and do it for each one of these if we like, but we can stop there as well. Let me take a look at a quotient identity as well. And so let's start off with, let's go sine, the easy one here, sine theta over cosine theta. So you know what? I wonder if this is going to be some kind of identity as we do this here. So by definition, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And again, you can cancel off the denominators right away if you like. All right, the proper mathematical way of doing it is you keep the numerator exactly where it is. You multiply through by the reciprocal of your denominator. In that case, it's going to be c over b. And then you notice, yes, the c's are going to cancel anyways. And you're left with a over b. And you ask yourself, you know, is there a trig identity that is actually a over b? Yes, it is. There is. It's tangent. So great. Now we've established another one. It is tangent theta is equal to sine theta over cosine theta. And there it is. There's another identity I have just formed. We're not going to go through the whole entire job of getting all of them. That would be too long, but here's all of them listed. It is on page 488 in your textbook, I believe. And again, there are 6 different reciprocal identities given. And then there are 2 quotient identities there. One is for tangent, one is for cotangent. So tangent is sine over cosine, as we just proved. And then we have cotangent is really cosine over sine, and you do it the same way. You would prove each one of these exactly the same way that we just did. All right, so what we want to do is we want to use these identities that we have just created, and just to practice here, it says let sine theta be 3/5, let cosine theta be 4/5, and then you need to find the 4 remaining trigonometric functions here. You don't really have to go in any order as well. And so we'll look at it here. I'm going to go with cosecant theta, just to sort of look at a little something here. If you say cosecant theta is technically 1 over sine theta. And that's by the identities we just created. And I can plug in now 3/5 for sine. But if I do that, it's 1 over 3/5, really just the reciprocal of 3/5, and how about 5/3? So there it is. Cosecant theta is just 5/3. Now, Do you need to go through all this elaborate process? No, you don't. I think you know how to take a reciprocal of something. So the quick fast way, if you know what sine is, you can automatically say, oh yeah, cosecant theta is 5/3. So if you know that cosine theta is 4/5, then you say secant theta is 5/4. That's pretty easy, just like that. All right, for the tangent of theta equals, now you're given sine and cosine, so you might as well use, kind of depends what you're given. So because you're given sine and cosine, you want to use the quotient identities. You say to yourself, you know, it's tangent theta is really sine theta over cosine theta. That's what it really is. So if that is the case, I'm going to put in 3/5 on top, 4/5 on the bottom. And in order to simplify this here, how about it's going to be 3/5 times the reciprocal, which is 5/4. The 5s are canceled. And we get ourselves 3/4. That is what the tangent value is. Last one is the cotangent. Cotangent theta is, now this one you can actually go one of two ways. You can go using the reciprocal identity of 1 over tangent. You can also use the quotient identities. Remember, cotangent and the quotient identities is cosine over sine. Whichever way I want to do it, go for it. You're going to get the same answer here. Since I just figured out what tangent was, I can just do the tangent one. That's probably easier too. 1 over tangent theta, that's the reciprocal identity, and I just figured out the tangent is 3/4. So how about cotangent has to be 4/3, and done. All right, next one here. So find the other 5 trigonometric values of theta, given that theta is an angle of a right triangle with cosine theta is equal to 1/3. All right, a little bit different than previously here. We have to form a triangle just given one trigonometric function. And so can we figure out the rest based upon that? Let's try it. First things first is let's set up our little triangle. And so setting up the triangle here, make sure it's a right triangle. Put a little block or a square in the angle that is 90 degrees. Now, based upon cosine, theta is equal to 1/3. First, I'm going to label my angle measurement, where it's going to be. It's going to be in the bottom right-hand corner. It doesn't have to be. You can actually choose the, bottom left-hand corner. You could choose the upper right-hand corner if you like. That'd be fine. But theta I placed in the lower left-hand corner. If that is the case, remember how cosine, by definition, is adjacent over hypotenuse. So in this case, the hypotenuse has to be 3, then the bottom adjacent side. And what we call by adjacent side is we're saying the side that's touching this angle. So hypotenuse, adjacent. Now, of course, we're missing this extra little piece right here. And you can either label it as an A or a B, whichever you like. I'm going to label it as a B. And we have ourselves a Pythagorean theorem coming up. All right, let's go for it here. So I know it's going to be 1 squared plus b squared is equal to 3 squared, as the Pythagorean theorem says. And square all the numbers I know. So how about 1 plus b squared is equal to 9. Let's subtract 1 from both sides. That will give us an 8. And I'll let you guys finish this one off here. Can you simplify this value right here? So I'm going to take a square root of both sides, and I'm going to keep it as positive, right? No need to do plus or minus square root because this is a length of a triangle and it has to be positive. All right, square root of 8 really doesn't that wind up to be, let's see, 8 is really 4 times 2, so 4 times 2. 4 is a perfect square of 2, so 4 gets to go on the outside as a 2, and the 2 stays inside as the leftover. So I got b value being 2 root 2. Okay, based upon that, now I think I can figure out all the other trig functions here. Let's go for it here. So sine of theta is equal to opposite over hypotenuse, and that is perfect. No need to do anything else there. I got it. Tangent is going to be, let's see, opposite over adjacent, but really the adjacent side is 1. Because it's just 1, there's no need to put it down even as a value. It's just 2 root 2. All right, cosecant theta now is going to be, now this is going to be the hypotenuse over opposite side. All right, in this case, we do have to simplify because we do not like those little radicals in our denominator right here. So we're going to multiply to get a perfect square. So multiplying by root 2 on top, root 2 on the bottom, and hopefully you guys have already finished it off. On top I have a 3 root 2. On the bottom I should have a 4, right? The 2 that was already here. And square root of 2 times square root of 2 became 2 itself, so 2 times 2 is 4. Secant is going to be the easiest one. Remember, it's the reciprocal of cosine, so really there's no work to do at all. What we do is we just take the reciprocal of 1/3, which is 3, and done. All right, and for cotangent, it's going to be, by definition here, adjacent over opposite. All right, and again, same thing that we had for cosecant here, is multiplying through by a square root of 2 both top and bottom, and we wind up with a square root of 2 over 4 as our final answer. All right, this is the next few slides here. We're going to be going through it. It's going to be somewhat important. We're going to use this for the next sections, in fact the rest of trigonometry here. So this is in a sense almost like the little groundwork for this. And I broke it up into different parts. So this part is the 45, 45, 90 triangle. It's part 1. There's a part 2, so you got to put your thinking caps on. This is going to be somewhat important here. Let me present it first the way I would present it, and then I'm going to present the book way, because there's just a slight little difference, but I'm going to present it this way because it's going to make sense for the next section as well. Or if we don't, then it doesn't make sense the way we do this here. So why is the 45, 45, 90 triangle so important? Is because if you go all the way back to geometry, you should have done this. You should have realized that if you have a 45, 45, 90 triangle, you can know the lengths of each of the sides. So what do we mean by that? So let's do this here. So the setup is this, is that you have a square. And you have a square. And then what you do is you draw a diagonal through that square. And the diagonal has a length of 1. Okay, so now the whole question is, can you know the lengths of the sides of this square just by knowing that the diagonal is 1? That's the question. All right, so first things first, let's see what we can figure out from here. So because it's a square, we know that's a 90-degree angle down there in the bottom right. Also, since we don't know what the value is, we might as well put an x. So since it's a square, we know that both sides have to be exactly the same of the square. So at least we know that. Next, we also know since we made a diagonal come through a square, what we really did is we cut that 90-degree angle into a 45-degree angle here and a 45-degree angle here. Okay, and really the question is this: can I somehow know what x is? Is there a way to know the exact value for x? Not an approximation, but an exact value. And so I think we do, because we have something called the Pythagorean theorem. So the Pythagorean theorem says a squared plus b squared equals to c squared. And if that's the case and it applies correctly here, we can use x as the a on the bottom. We can use x as also the b for the side, and then we have our c value, which is 1, being squared. So notice if you can get this, doing great here. So let's see. I'm going to square both sides, so that gets me an x squared plus another x squared is equal to 1. Adding both of them together, does that give me a 2x squared is equal to 1? All right, and let's see if we can solve this here. First and foremost, I can divide both sides by 2. So how about x squared is equal to 1/2? Then I'm going to take the square root of both sides. And again, I don't need to do plus or minus, because the length of a side of a triangle or a square, therefore it has to be positive. Okay, if I do that, I can split off the square root, one to the top, one to the bottom, and for the top value, square root of 1 is just 1. So I got x is equal to 1 over root 2. Now, real quick here, I should tell you that sometimes the book is going to use this right here, 1 over root 2, as the value, because it's simplified. It's simple in its form. And you can do a few things with that real easily here. But for purposes here, what we're going to do is we're going to rationalize our denominator. So let's multiply by root 2 on top, root 2 on the bottom, and how about a root 2 over 2? That is the value that we get. Okay, why is this all special? Is because we were able to figure out the length of the side, particularly when the hypotenuse or the diagonal was 1. All right, what do we say? We say x is either 1 over square root of 2 or x is equal to square root 2 over 2. And again, we're going to use both of those. You should be sort of familiar to see both of those there. All right, keep that in your mind. Again, we'll practice some more. Really, the use of this is going to come in the next section. Now this is the 45, 45, 90 degree triangle part 2. Now this is the way the book presents it. So why am I doing it this way? Why am I doing it both ways? Because the part 1 way is going to be useful for the rest of trigonometry. The part 2 way is very, very useful sort of for quick calculations. And so that's what the book uses. So a different little setup here. We still have our little square. We make a diagonal coming straight through the square. But this time, let's see, right triangle is fine. This time, and for the previous one here, it's 45 degrees over here. Let's label a few things here. It's 45 degrees up there. Is the fact that each of our sides is 1 unit. So now the question is, if each of the sides are 1 unit, can you figure out what the hypotenuse is? That's really the question. So let's put an x here for the hypotenuse. And of course, you should think about, oh, Pythagorean theorem should help here. So let's go for it here. A squared plus b squared is equal to c squared, and plug it in. See if you can get ahead of me. That'll be fine as well. So a is a 1, the b is a 1. Squaring that gives you x being squared. So 1 plus 1 is equal to x squared. So 2 is equal to x squared. Okay, again, let's take the square root here, the square root there, and we get ourselves the square root of x, square root of 2 is equal to x, and then we don't really like to have it that way. We like to turn it around. So x is equal to square root of 2. So on a 45, 45, 90 degree triangle, if the sides are 1, the hypotenuse would be square root of 2. And again, why do we use part 2 here? Is it gives you quick calculations, and notice there's no fractions here. That's really the major issue here. There's no fractions here, but again, I prefer to see the fractions here because we're going to use the fractions later on quite a bit. All right, so if we just want to write it all out here, if you have a triangle that is a 45 degree, 90 triangle, and if you have the sides as length 1, therefore the hypotenuse will be length 2, or square root of 2, sorry. All right, then we come to the other one here, the 30, 60, 90 triangle. And again, it's part 1. This is the one that's going to include fractions in it, and again, it'll be helpful later on. Then we have a part 2 on our hands as well. All right, where does this come from? This comes from geometry again, and this comes from the fact of thinking about an equilateral triangle. If you have an equilateral triangle, all right, we know that then each of the sides is going to be 60 degrees. Right? Equilateral triangle. It means that all the sides are the same, but also it means each of the angles are 60 degrees. And here's what we're going to do. We're going to say, what happens if each of the sides of our equilateral triangle are 1? And then, what happens if I drop down a altitude from the top angle straight down so it hits the bottom side perpendicularly? So now what you have is you have a 30 degree triangle. So now here's your 30, 60, 90 triangle. That's where this comes from. All right, now the question is, what's the length of this part right here? So if you put an altitude down for an equilateral triangle, what will be one of the sides worth? And I think you guys already know it here. It's going to be worth exactly half of the other side because it's going to break it up exactly into a congruent triangles. That's what's going to happen here. If that's the case, then it has to be a half. But we got one more little area here to give. We don't know what the length of the altitude is. So now the question is, can you find for me the length of that altitude? All right, and again, all we got to do is set up a Pythagorean theorem. In this case, how about 1/2 goes for the a value, how about the x goes for the b value, and how about 1 is the c value? And again, if I'm going a little too fast, you can pause the video if you're watching it at home here. And if you're in class doing this with me here, please tell me to slow down or wait. Let me wait for you to catch up here. All right, here we go. But 1/2 squared is going to give you a 1/4. X squared is just going to be x squared, and 1 squared is 1. We're going to subtract 1/4 from both sides. Hopefully you guys can do that in your head here. If you have 1 and you're going to subtract 1/4 from it, or a quarter, you're going to be left with 3/4. Solving for x, we have to take a square root. Again, forget about the plus or minus because we're looking at distance here. Therefore, it has to be positive. All right, let's split it off. Split it off to the top is 3. To the bottom would be a square root of 4. And final answer here, how about x is equal to the square root of 3 over 2? So there it is. I'm able to know the exact values. Now, the interesting thing is in geometry, we understand that there are no other triangles we can form besides the 45, 45, 90 and the 30, 60, 90 triangle that we can actually know the side lengths of. The rest just don't work. So these two triangles are extra special. And we're going to use these principles of geometry. We're going to bring all this in and form a whole new branch of mathematics called trigonometry, which is cool. All right, so if we just want to label this here, we're going to say if I have a right triangle, one side is 30, the other side is 60. The hypotenuse is 1. If the hypotenuse is 1 off of this, that means the side that is opposite my 30 degrees is going to be 1/2. And the side that is exactly opposite my 60 degrees is going to be √3/2. So that's the way I usually think it's probably the easiest way to do it. So that gives me the shorter side, and the reason I know it is because of this right here. When we split that angle in half, we get ourselves a 30-degree angle here, but it's going to give us a 1/2 off that side. All right, and then opposite my 60 will be the value that we just figured out, which is √3/2. All right, you can also think of it as another way here. Another way is the 30 being on top and the 60 sort of being on the bottom. If that's the case, see if you guys can label each of the sides just really quick here. Go for it. I'll give you guys a few seconds. All right, the hypotenuse should be 1. And again, the side that's opposite the 30 degrees is 1/2. The one opposite my 60 degrees is √3/2. There it is. So from here, we kind of use both of these angles here. We kind of use the 30, 60, 90. We use somewhat like a 60, 30, 90 triangle as well. So just make sure you can sort of move these around in your head a little bit here and know where each of the side lengths are. All right, so we have part 2. All right, this is from the textbook here. This is the way the textbook does it. And again, what the textbook is really trying to do is get rid of all the fractions. That's all. So we set up the same exact triangle. We know that each of the angles will be 60 degrees. And then each of the sides are going to be 2 this time instead of 1. So because each of the side lengths are 2, let's see what happens here. We drop the altitude. Perfect. That means this is going to have to be 30 degrees now. No other way around it. This part here, because it's just broken up in half, so 2 divided by 2 is a 1. All right, this is x because we don't know it. And we're going to plug into the Pythagorean theorem. A squared plus b squared equals c squared. Let's go for it here. So the a value is 1. The b value is we don't know, which is x. C value is 2 being squared. All right, so that's 1 plus x squared, and 2 times 2 is 4. That's perfect. Subtract 1 from both sides, and how about square root of 2 is equal to 3? And we're going to take the square root of both sides. Again, keep it positive. We have x is equal to √3. All right, so we know what that is now. And again, if you want to label this, just let's quickly label this. Let's say you have a triangle, a right triangle, in fact a 30, 60, 90 triangle, and all you know is the side that's opposite your 30 degrees is 1 this time. Can you label the rest of it? Well, this one is very similar to the previous one here. So again, this is the same exact angle that we have, triangle that we have here. So that means this has to be 1. The hypotenuse has to be 2, and the value that we just figured out has to be square root of 3. Okay, so let me do this here. Let me move this just around just a little bit. I'm going to go like this here. I'm going to put this little label like this. There's my right triangle. I'm going to label this guy as the 60, this guy is the 30. And again, I got to give you one of those values here. And the hypotenuse is 2. All yours, a few seconds. Can you give the length measurements of the other 2 sides of the triangle? All right, hopefully that was a little bit of time here. So opposite my 30 degrees should be 1. Opposite my 60 degrees should be √3. So there it is. All right, practice problem number 4. Let's go for it here. So use figure 5.23, which is right here on the right-hand side. Can you find cosecant of 45 degrees, secant of 45 degrees, cotangent of 45 degrees? So notice, well, I'm just giving you a angle measurement. That's it. There's no tying to a triangle, even though we are going to tie this to a triangle. But we should see that the problem itself is just giving us an angle. That's it. All right, let's choose which one. Which angle we're going to use. And let's go for it here. So cosecant of 45 degrees. It's going to be, by definition, if you want to write it down, that's fine too. Remember that the definition is hypotenuse over opposite. So if we're looking from the bottom left corner, the hypotenuse is the square root of 2. Opposite side, which is 1, which really is just going to be square root of 2. Secant is 45 degrees. Again, by definition, hypotenuse over adjacent side this time. Hypotenuse is the square root of 2. Adjacent side is 1. Therefore, we have ourselves the square root of 2 as our final answer. And cotangent. Cotangent of 45 degrees. By definition, adjacent over opposite. So how about adjacent is 1, opposite is 1, therefore we just get 1. All right, practice problem number 5, just practicing now with the 30, 60, 90 triangle here. Can you give me all 6 trig functions of 60 degrees? So we've got to think about what you're looking from. According to this figure, we're going to look right here from the bottom right-hand corner this time. And sine of 60 degrees equals opposite over hypotenuse. So the square root of 3 over 2. Cosine 60 degrees. This would be, let's see, adjacent over hypotenuse, or just 1/2. Tangent 60 degrees. This is going to be opposite over adjacent, so opposite of root 3. Adjacent is 1. At this point, let's not even write it down. There's no point to write it down because it's just going to be 1, so it'll be still just square root of 3. Cosecant 60 degrees. Putting this together here, this is going to be hypotenuse over opposite. And again, notice we have to rationalize our denominator. So multiply root 3 on both sides, top and bottom. So now we have 2 root 3 over 3. Secant of 60 degrees. Oh, that's even easier. You know, we could go by definition. We can look back at cosine. It's even easier to look back over here. Cosine is 1/2. Therefore, secant is going to be 2. Might as well just do that. A lot easier. Cotangent of 60 degrees. All right, definition here is adjacent over opposite. In this case, yes, we do have to multiply through by the square root of 3 over square root of 3. Sorry, the last slide here, the answer was the square root of 3 over 3. So square root of 3 over 3. All right, so if we're to make a little table of all these here, so if we look at 30 degrees and we look at radian equivalent of it, is pi over 6, which we looked at in the last section here. And then what we do is we just label these each. Okay, 30 degree, Why is this important? Because we're able to get exact values of our ratios. 45 degrees, here it is, exact values of the ratios. 60 degrees, exact value of the ratios. All right, so of course, you kind of look for patterns here, particularly for the sine and cosine. Notice what happens with sine. Sine starts off with 1/2, and it goes to square root of 2 over 2, then it goes to square root of 3 over 2. The cosine works the exact other way. Starts off with root 3 over 2, goes down to root 2 over 2, then goes down to 1/2. And so these are the common angles values. We'll practice some more as we get into a little more of in trigonometry about all this, and you'll see it quite a bit. All right, as I stated before, this whole concept of what does it mean to be a cofunction? And so we say sine and cosine are cofunctions of each other, and the reason for it comes from the word complementary. Remember complementary from geometry? Complementary angle is an angle that adds up to give you 90 degrees here. So we have all these little rules here that says sine of a certain angle is going to equal the cosine of the complementary angle. Same thing here, cosine of an angle will equal the sine of the complementary angle. So tangent, cotangent, again, they're cofunctions of each other. Secant, cosecant, again, cofunctions of each other. So let's practice just a little bit with this. So given that cosecant of 21 degrees is 2.1904, can you find secant of 69 degrees? And again, you're just sort of just practicing. That's all you're sort of doing. And then we'll do B as well. So if this is the case, cosecant of 21 degrees is approximately 2.7904. We need to figure out that cosecant of 69 degrees is, well, technically speaking, you would say it's the same thing as cosecant of 90 degrees subtract 69 degrees. And you got to do a little bit of work here. This is going to be cosecant of 21 degrees. And we're given the approximation for cosecant of 21 degrees, which is 2.7904. So again, it's just one of those, just practicing with it. All right, if we know the tangent of 75 degrees is approximately 3.7321, can we figure out what in the world is cotangent of 15 degrees? Yes, absolutely, because cotangent of 15 degrees is the same thing as tangent of 90 minus that 15 that we have there. And if we do that, we wind up with tangent of 75 degrees, and that is given already approximately 3.7321. And again, this is just almost in a sense just for practice sake. All right, we have some application questions here. I'm going to skip this section just because of time constraints here. Just if you need to know the angle of elevation, if you're looking up, it's called the angle of elevation. Angle of depression means you are looking down. Again, we'll take a look at those next time.